Hello. Today we're going to talk about the second part of colligative properties. And in the first part, we talked about Raoult's law and vapor pressure. We did a couple problems. And before that, I had just given a little overview of these four colligative properties, and we talked about just how they change. So to review that, these are properties that just depend on the number of solute particles. So the colligative is kind of just like a term for how many particles you have. So you can think about the greater the number of solute particles in the solution, that's going to determine the extent of these properties. And if you remember from number 5 from this handout, the more solute particles we have, the lower the freezing point, the higher the boiling point, the lower the vapor pressure, and the higher the osmotic pressure. So 2 of these go down, 2 of them go up. These are the respective equations. We'll go over a couple of these in the next problem. And if you can also stare at the equation and kind of figure out the concepts just from how the concentrations change or the I value changes. The one that you'd have to maybe think about a little more is the vapor pressure, which we talked about, because if you increase the mole fraction of the solute, that means the mole fraction of the solvent goes down, which is what you're using in the formula, and that's why the vapor pressure goes down. This number is actually decreasing. And then, so in the other ones, you just basically have concentration of solute, either molality or molarity. So we have number 9, calculating the boiling and freezing point or temperatures of this sodium fluoride solution in water, aqueous solution of the salt. In these formulas, you'll notice that there's a lowercase m, which is molality. So we're going to start by finding that concentration unit. And if you remember, we need the moles of solute over the kilograms of solvent. So we're going to divide the 10 grams of sodium fluoride by its molar mass. This is the solvent down here, which we want to be in kilograms. So that's just an easy conversion. But remember, this is just the solvent. So it's moles of solute over kilograms of just the solvent. And this comes out to 4.8 moles of sodium fluoride over kilograms of water. Okay. So in either of our formulas, it basically looks the same, where it's like delta T, I, K, M. If we're doing a boiling point, then it's going to be a positive change, and then we just use the K for the boilings, which is KB. So when we plug these numbers in, the I value, the Van Hoff factor, is only relevant if it's ionic. And if we remember from strong electrolyte ideas, this being a salt and a strong electrolyte will dissociate into 2 ions. So therefore, we have an I value of 2. So we're going to plug that in. Plug in our KB that's given. It's 0.51 degrees Celsius, kilograms over moles. And then the molality. So the units cancel, we get Celsius, 4.9 degrees Celsius. So is that our answer? This is the change in boiling temperature. So the boiling point is going to be the normal plus the change. So it's going to be, for water, 100 degrees plus this. So we end up with 104, about 105 degrees Celsius. So salt water will boil above the normal boiling temperature, a little bit warmer. This is a very salty solution, by the way. This is like 20% of the solution around is salt. So you actually need a ton of salt in your pot of water to make it boil this even just 5 degrees warmer. So it's kind of a misconception that throwing some salt into your boiling water or into your water will make the water hotter when it boils. It will, but it's pretty small effect unless it's, like I said, extremely salty. For freezing point, there's a greater effect, and this one we do have a negative. Sometimes this negative isn't given, but it indeed is a negative or decrease in temperature. So you might want to just always think about, if you don't see it, just put it in there in the equation because it should be there really. So we have negative, and then I again is 2 for sodium chloride. Here's our Kf, and then our molality, I'll just leave out the units. This is negative 17.9. So you can see this is a bigger change. The freezing point depression is larger than the boiling point for water. So again, we have our normal freezing point plus the change. Kind of nice because for water it's just 0. So we just subtract from 0 to get the same answer. Kind of foolproof. Okay. Interesting in this sense because this is used commonly with places where they have an actual winter. Heard of these places. You can put salt on the road when it gets around freezing temperatures, and it'll prevent ice from forming because the temperature has to get a lot colder for it to freeze. So salting the roads is a common application of colligative properties. And the last one, we're just doing a conceptual problem with osmotic pressure, although this could be really for any of the colligative properties. And in this problem, we're going to look at, these are all the same concentration. So then again, with the osmotic pressure, this is what the pi means, it's osmotic pressure. Then because the other two are essentially constant, we're assuming the same temperature for all of them. It's just this factor right here, I times molarity, I times the concentration. So the higher the I times the M, that means a larger osmotic pressure. And since this is the same for all of them, then it's really just whatever one has the greater I value. So if we go through these, this is sugar C6H12O6, a non-electrolyte. That's a term that, if you remember, does mean it's essentially not ionic. It does not dissociate. I is always 1 for those, also called molecular covalent compounds. And then we have a couple ionic compounds. So this will break up into 1 calcium and 2 chlorides. This will break up into 3K. I'm going to write it up here. Calcium plus 2 chloride. This is going to be 3K plus and 1 phosphate. So you're going to get 4 ions. This is a strong acid, if you remember. So you're going to get H plus and Cl minus. And I kind of just threw this one in there for a little bit of a different kind of solute. Not strong electrolyte, not a non-electrolyte. This is a weak acid. And acetic acid, if you remember from Chem 1B, it will partially dissociate. So what we get is that a small percentage of it breaks up. And without doing any kind of math, which we don't really need to do, just would know that it would be somewhere between 1 and 2. In other words, if you think about not dissociating or dissociating completely, it's in between that. That's all we really need for this problem. So then we can just arrange them. This would be increasing osmotic pressure. We would have the sugar, C6H12O6, the lowest. Acetic acid solution, HCl calcium chloride and potassium phosphate being the highest because the most solute particles in that solution. So I mentioned this could be for any colligative property, not just osmotic pressure. And again, if we go back to the concept, in this order, you have more particles, right? So this is more solute particles. So what would also be increasing that way would be boiling point, increasing lowest to highest. But the freezing point would be going the other way. So in other words, the potassium phosphate would have the lowest freezing point. And as we get closer to the sugar, that's closer to pure water, closer just to normal freezing point. And also vapor pressure would be lowest for the potassium phosphate. So once we get kind of the number of particles and those in order, then again, any of these four colligative properties are in order. We just have to figure out which way it's going, to the right or to the left. So I would recommend not actually like calculating these things for each of these. It's just a lot of work that's unnecessary. You can just think about the concepts, and hopefully if you have a problem where you're putting it in order, that's all you need to do. And definitely let me know if you have any questions or on working out any specific details of the formulas or numbers. I'm happy to help you with that. And I'll talk to you next time.